Everyone, good afternoon. As people are trickling in, I'm just gonna get started here. So my name is Daniel Calzada. I'm a recent graduate from the University of Illinois with a master's in computer science. And today I'm gonna be presenting as the last research presentation my prediction algorithm called DeepBall. So what I'm going to be presenting here is a summary, a condensed version of my master's thesis. So if you like the full thing in its 60-page glory, you can go to our website, and there's a link for it there. But I'm just going to be giving you the highlights. So what is DeepBall? So DeepBall is an algorithm for predicting preseason player performances. So if you've heard of Steamer and Zips and Marcel and Pacoda, it's kind of similar to those, except it's different in a few ways. And I'm going to get into these more. First off, it's built using recurrent neural networks, and second of all, okay, and second of all, it's built almost exclusively using retrosheet data. So kind of an overview of where we're going to be going. I'm going to talk a little bit about the background, about the motivation to this problem and why it's interesting. I'm going to talk about where we're getting the data from. I'm going to talk about how the model works and how it performs on real-world data. And then after that, I'm going to talk about some extensions that we can take to this model and see what else we can have DeepBall answer for us. Before we get started, I'd just like to give some acknowledgments. First off, my thesis advisor, Sammy Coelho, without his willingness to learn a new domain for him that is baseball, this wouldn't have been possible to do and for me to present now. I would also like to thank the DeepBall team, Clark, Tyler, Ashley, and Tyler, who have helped after the research has been done to kind of build out our website. So if you like our website design, you can thank them for it. And lastly, it's not written here, but thank you to the SABR staff who have worked very tirelessly to put this conference on, and just for the high quality of presentations that we've seen so far. So here's a fundamental question that I want to ask as we're kind of thinking and formulating this problem. How much baseball research do we need in order to build a good prediction? So it's kind of conventional knowledge in baseball that in order to predict the future, you have to really know the game of baseball well. And you have to study things like aging curves, advanced metrics, and so on. But I want to kind of try and challenge that and try and build as good of a model as possible with as dumb of a data set as possible. So we're going to try and answer that. So here is a traditional approach to the preseason player prediction task. So it's kind of a pipeline. You start with the data, right? And hopefully the data is driving your whole process, but it's for sure the foundation. Then you start to analyze. If you're trying to make a player's prediction, you first have to analyze their past and their history. What happened first of all, and second of all, why did it happen? Can we kind of get beyond the surface level numbers and actually start to understand this player's history? Once we've gotten there, we can move into examining the player's present situation. Where are they at now in their career? What are their strengths and weaknesses? And from there, then we can build out our future prediction if we have that fundamental understanding. And we can take in things like park factors and their age and how players typically age and kind of bring that all together into one final output. So there's some issues here. First of all, it relies a lot on human bias. So as we've seen it, as the sabermetric community and research has kind of evolved, our understanding of the game and what makes a good player has changed. And it turns out if we bake in our biases into the previous steps, we're going to have a propagation of errors that goes all the way into the output prediction. So if possible, we want to find out if the data itself can just tell the whole story without us adding in our preconceived notions. So to that end, DeepBall takes a more direct approach. It goes straight from the data and models directly what we expect from the future. And it's worth mentioning that it probably models the middle two steps there somewhat implicitly, but we're not actually going in and telling it, here's how we think a player should progress throughout his career. So with a data-driven approach like this, it's clear that the data that we have is going to be critical. Good data equals good model, hopefully. So we have to talk about then where are we going to get this data and how are we going to do some pre-processing. So first off, for the data sources that we have, we're primarily, as I mentioned, relying on RetroSheet. So RetroSheet is a giant play-by-play database that goes all the way back pretty much to the start of baseball. It blew my mind when I first found out about it that this is actually a thing that exists. So what we did is we took this play-by-play and we broke it down and built some aggregates, how just the player season totals. And from this, we kind of derived more advanced quote-unquote metrics, such as park factors. And we took in things that RetroSheet has, like batted ball types, and in cases where it has it, plate discipline, so number of swings and misses, called strikes, and so on. We also bring in a bit of the layman database with biological information, and we bring in some sabermetric information, such as wins above replacement, as inputs from Baseball Reference as well. And you might be wondering, is that kind of violating the hypothesis of only using surface level stats? Kind of, but that's all right, because it doesn't actually build a whole lot, and it doesn't add a whole lot of benefit, but it still adds some, and we want to take advantage of that. And the last bullet point here is something I want to point out. So we're only using Major League Baseball regular season data. So no minor leagues, no postseason, and of course we know that if we know someone's minor league stats, we could predict them a little better, and perhaps postseason play could affect their performance on the next season. Who knows? These are things that we can that are topics for future research. But for now, this is all that we're dealing with. Okay, so with DeepBall, as I mentioned, again, it's a supervised machine learning algorithm. So if it's going to work, we need a lot of data and good data. So to that end, we use data including rookies or players who have debuted since 1958 up through the previous year that we're trying to predict. So now that would be 2018. And while that sounds like a lot on its surface, there's actually only, if the last year there is 2014, there's actually only around 8,000 unique batters and 45,000 unique batter seasons, which is not too many. And it gets even worse when you consider that a lot of those seasons are very few plate appearances. For example, a relief pitcher in the National League, he's going to be in that 8,000, even though that's not actually very useful data. So we're going to talk in a little bit of how we actually go about dealing with the issue of limited data. The other thing that we have to talk about when we're talking about prediction is what are we actually concerned about modeling. So again, most of these stats here are surface level stats. We have typical stats, batting average, slugging percentage, some plate discipline stats, as well as playing time. And we want to try and examine if, just from one player's stats, if we can get a good model of how much they're going to be playing. And we also have, as a kind of aggregate, we have the offensive wins above replacement that we're trying to predict as well. The idea of designing and using these stats is that they kind of give a big picture over the batter's entire game, plate discipline, batting and batting styles, and player value. Okay, so enough about the data then. How does this model actually work? So if you're familiar with deep learning, this should be kind of a review. If not, that's all right. So what we're using here, as I mentioned, is called a recurrent neural network. So the idea here is that we want to model a player's entire career as a sequence of seasons. And we're going to design a model that takes in ground truth from the previous years and uses that to predict what happens in the next year. One benefit of using this is that we don't have to specify how far back we want to look. In a player's career, I know a lot of prediction systems look at 3 years back, 4 years back, 5 years back, and throw out the rest of the data. And we're basically just telling the model, hey, we don't care, use whatever you think is reasonable. So, for example, we can, if we're trying to make a 2018 prediction, we will digest the player's entire career up through the end of 2017 into one vector. And then we use that vector to try and generate the 2018 results. And of course, we can't actually use the 2018 results because that would be cheating. So what we have here is, and once we draw it all out, the model here is very complex. There's something on the order of 70,000 unique numbers in this model called parameters. That if you change one number, the entire model might change. So we have a very big model space, and we have a very small amount of data. So if you're familiar with machine learning, you'll know that this is a big problem. So how do we go about trying to solve this? Well, one way we do it is through model bagging. Too many models, false, there can never be too many models. Before you start throwing stuff at me up here, that's not actually entirely true. It's true in theory if you have unlimited data. If any of you can find a way to get unlimited data, please let me know. I would love that. But in the meantime, we're not dealing with that now. So what we are going to do, though, is train a bunch of models on the same data set and try and combine those models in some way. Because the thing with neural networks is that even if you keep the architecture of them the same, all of those 70,000 parameters, you have to start them at some number. And normally what people do is just start them at some random values. Now it turns out that depending on which random values you choose, you can get an entirely different prediction for the exact same player. And that's kind of what's called variance. That's not a good thing, and we want to try and reduce that. So what we do is start a whole bunch of models with the same architecture, but different starting points, and we train them all, and then in the end, we can combine them into one model. So what I have here is the weight matrix. So for each stat, each model gets a different weight. So you can draw a few things from this matrix. You can see that model 8, all the way on the right side, in general is a little bit better, and the darker values in that table mean that the model got more weight. So you can see the 8th column has, in general, more weight, and we can also see that some models have different strengths and weaknesses. And again, why does this happen? We don't really know, but it does, and we want to try to use that to our advantage. Okay, so now you're probably wondering how this very abstract and kind of dumb approach is going to work on real-world data. So in order to establish that, we need to establish some baselines first. So some of you, I'm sure, are familiar with Marcel. It was developed by Tom Tango for this specific task. So what Marcel does, basically just takes a linear combination of the player's the previous 3 years, adds just a basic aging factor, and regresses towards the mean, and that's it. So it's named after Marcel the monkey. The idea is that it's the bare minimum that a prediction system should be able to accomplish. It sounds simple, but a lot of people have spent a long time trying to beat this monkey, including myself, and have spun their wheels to no avail. So it's simple, but it's surprisingly good. It shows how difficult the problem actually is. The second baseline that we're using is a traditional machine learning method that was alluded to in the previous presentation, a random forest. And a random forest can't deal with variable length sequences of data, so we just chop off and just look at the previous 4 years of data when trying to make those predictions. And then the last thing here is what I'm just calling the Simple Rnn Model. So the idea is that this is a dumb version of an RNN. So what we do is we take all of the players' previous inputs, their entire career, and all of their stats. We glue them together, and we send them into a recurrent neural network and see what happens. You can kind of think of it as the Marcel of deep learning. We intentionally tried to make it as simple as possible. And as you'll see, well, I'll leave that for a little bit. So the methodology for testing this, we're using 2015 through 2018 as test data. So, and because of the issue of limited data, and also because of the changing strikeout rate that we observe, we have, in order to make a prediction for year X, we train a separate set of models that uses data up through year X minus 1. So for example, to test our model on 2017 data, we train a model from 1958 through 2016. In our evaluation, we only include position players, though DeepBall can predict the offensive totals for pitchers too. If that's something that people actually want, I doubt it, but it's there. It's there if you want it. So in the end, we have just shy of 1,000 batters and just shy of 2,500 batter seasons. And here are the results. So what we have here is we have the mean squared error of each system, and it's normalized relative to league average. So the average prediction is a 1, and a 0 is scaled down to a 0. And the percentages there are relative improvements on Marcel. So for example, a 10% there means that it has 10% less error than Marcel. So you can notice a few things here. First off, the random forest is not very good. It actually does a lot worse than Marcel, so don't use that. And we also see that DeepBall here, thankfully, does the best out of all of these baselines. There's something interesting, though, that I want to point out here, and that's the relatively small difference between the recurrent neural network and DeepBall. So the difference between those two is the primary source of domain knowledge of baseball research that is in this model. So with DeepBall, I tried to tune like which variables should kind of interact. For example, park factors and player stats I thought should interact pretty closely, whereas base running stats, maybe they wouldn't have the same relation. Whereas the simple Rnn, it just treats them all the same. So we can see that research does add something, which is encouraging to us as researchers, knowing that our research is useful for making these predictions. But we can also see that even just with a simple model, we can still achieve good results. And just for completeness, here's what it does on the count stats. So plate appearances, games, and wins above replacement. So we see, again, a similar ranking here, with the exception that Marcel does by far the worst. And we attribute that just to the simplicity of Marcel's design. It's not designed to be cutting edge. But again, DeepBall does the best in all three categories, and the Rnn is a close second. So now that we've established that we have a good technique, at least according to these baselines, for modeling predictions, preseason predictions, we're going to switch gears and talk about the big picture. So here's another question that I want to ask. Can we know how much we don't know? So here's an example. The DeepBall prediction system might say Chris Bryant is going to bat .273. And we all know that it's not going to be, probably not exactly 273, right? There's going to be some window on either side. But how can we actually quantify that window? And better yet, is that window actually useful? Would some players have a greater window than others? And how would we be able to interpret that? So we're going to move beyond just the modeling of the expectation, the point-wise prediction, and move towards modeling a general uncertainty model. So what we're going to do here is, instead of just predicting a point-wise prediction for these 8 stats, why not just model a fully defined probability distribution? So here's an example of a Gaussian distribution, and you can see there very clearly that all 4 of those examples include both a mean, a center, and a spread. So of course we want to model the mean in the center of that distribution, right? What do we think the player will actually do? But also we want to model the width of that spread. And another thing we might want to model is the covariance too. So how are these variables correlated? And you might see some players, for example, J.D. Martinez, whose value comes predominantly from power. How might his correlation between batting average and slugging percentage be different from, say, a contact hitter? Now, there's one issue with doing this, is that all 4 of these are symmetric. So in other words, if we were to say someone is going to play in 150 games this season, we know that that distribution is not perfectly symmetric. He's much more likely to play in 100 games than he is to play in 200 games. But right now, if we just use a single Gaussian, it would say that both of those had the same chance. So a natural extension of the Gaussian model then is to model a mixture of Gaussians. So what we do here is just take multiple Gaussians. In this case, we're just using 8, and we combine them with some linear weights, and those weights are learned, of course. And from this, as you can see in this picture, if we just add them up, we can get an asymmetric distribution. And this distribution here is pretty general. It's still not perfect, but it gets us most of the way there. So now our prediction task has moved just from modeling these single points into modeling the whole spread of variance and all of the parameters of this probability distribution. So here's some examples of this running in practice. So these are some predictions for 2019, and I pulled them up for Chris Bryant just in 2 stats here. We have his slugging percentage prediction curve and his plate appearance curve. So in his slugging percentage curve, you'll see that it's pretty uniform. It's pretty symmetric. It kind of has a little bit of a negative tail there, but it's not too much. So it's basically saying we're pretty sure that Chris Bryant is going to be around this, or around the slugging percentage, and we can also see the width of that spread. The plate appearance plot is kind of as you would expect. It's skewed positively. So perhaps because he was injured for part of this last year, or this is just how it generally predicts players, it does give him a negative spread here. So it's basically saying there's a half decent chance that maybe he's hurt again, and that will affect his performance. And that's showing up in this prediction here. Whereas if we just had a point-wise prediction, it might say he's predicted to have 550 plate appearances. It misses the whole rest of the story here. And here's a slightly more interesting example. This is with Ian Happ, the Cubs center fielder. So you can see from his plate appearance plot, and again, a typical prediction system might say he's going to have 450 plate appearances. But really, once we examine it a little deeper, we can see that really the model is saying we have no idea how many plate appearances he's going to have. It would be justified to say anywhere between 150 and 650. And just looking at his previous stats, we can't tell that. Now, of course, if you were to be able to examine the entire Cubs team as a whole, your predictions might change, but we're leaving that as another topic for future research. We can also see in his offensive wins above replacement plot here that the most likely outcome is somewhere between like 0.5 and 1, but he does have a very long, in this case, it's a positive tail. And what that means is that there's a good chance if he's going to err from that 0.5 to 1 range, it's probably going to be on the positive side. So why is this useful then? So why would this be useful both from a fan perspective and from a team perspective as well? So one thing that we can do, and this is more from a fan perspective, it's just kind of a fun thing, is we can visualize players. So what we've done here is we've taken all players, in this case all third basemen, just so the plot would be somewhat readable, and we examine how different their distributions are using Jensen-Shannon divergence. So then once we have that, and it's called a dissimilarity matrix, where we have for every pair of players how different they are, we can go ahead and visualize this using a method called t-SNE. And you can see that, well, it's hard to read the names there, so I'll just try and read them out. Here in this cluster is, we have Nolan Arenado, we have Travis Shaw, Eugenio Suarez, Chris Bryant, and Matt Carpenter are kind of all in this cluster here. And if you were to examine their predicted distributions, you see that they're pretty similar. And this kind of matches our intuition that we'd expect similar things from these players. Here in the bottom, you see Alex Bregman and Jose Ramirez, so they're basically the same point. And if you were to examine their predicted distributions, they're basically the same. So in other words, if I gave you a slash line at the end of the season and I asked you, was this from Bregman or Ramirez, you wouldn't be able to tell me. They're just that indistinguishable. So another thing that we can do is we can take all of the models that we've done and combine them, again, using the same weighting scheme, and compare them to Steamer and Zips. So that's what we've done here, and I'm going to show the results in a second. I just want to add some caveats. So first off, we are only looking at players with more than 2 years of experience. That's because we're not using minor league data, and Steamer and Zips are, so it wouldn't be fair to compare them. And also the analyses are relative to league average. So in a sample size of 846 batters, again, the table is formatted the same way, you can see that DeepBall does do the best in all 5 categories, and in some categories, it's by a wide margin. So if you're looking for just a single point-wise prediction for a certain player, this might be a way to go. And the player has 2 years of experience and so on. There's a lot more applications here that I'd love to talk about, but for the sake of time, I can't. Multi-year predictions. So this is something that would be useful for a team if you're evaluating if you should make a potential trade. You can train separate sets of models that predict instead of 1 year out, 2, 3, 4 years out, and so on. You can use the second point there, you can use the distributions to run simulations. So because it's a fully defined probability distribution, we can go ahead and sample from those distributions, and we can expect that those samples might be something that we could reasonably expect from that player. We can also use this to generate over-under thresholds, which are in general not going to be the same as the mean predictions, because like we talked about, predictions in general can be skewed. We can extend this to pitchers as well. So we host pitcher predictions on our website, which is very simple. Just throw pitcher stats into the batter model. And for some reason, it does fairly well, and we'll take it. And the last point there is that there's a lot of things that we can't even cover now, and maybe some of you here will come up with the next application for this methodology. So hopefully you've seen that DeepBall is able to take the surface level data and build that into a good and reliable prediction system. And from that, you can also extend DeepBall into various other prediction tasks that it can otherwise do in the first place. So thank you all for your attention. Maybe one question we'll have time for. Yes, Dick. Absolutely, yes. So the question is, can we baseline the like how wide we would expect the spread to be, right? Kind of to find a minimum. Is that okay? So there are some theoretical minimums that, if you make some simplifying assumptions, you can arrive at. Unfortunately, there's not really a system, as far as I know, that's doing this exact thing. So we haven't been able to explore that in a whole lot of depth. But that is another area. Again, it's another application that we could take. But thank you. That's a good question. Thank you all.